Okay, welcome to another video on AECPRE2. In this section, we will see the remaining two circuits where we are asked you to find the frequency at which output is 1 over root 2 times the input. So there is a specific reason asking for 1 over root 2 times the input voltage. Okay, these two are the circuits, and of course since the two capacitors are in parallel, they are going to add up. Here two capacitors are in series, so their effective capacitance is lesser than the least one. So here it is just the addition of these two. Here also I am asking what is the frequency at which output voltage is 1 over root 2 times the input, that is Vs by root 2. Okay, as you look into the solution, so as we saw in the first video of the second solution or second task, okay, this it goes like this. Okay, this is your given circuit, so that can be simplified and rewritten by considering these two capacitance as parallel capacitance. Then equivalent capacitance is this, and output voltage V0 is given by, of course I am writing just the magnitude of it. So when I say okay, magnitude of it magnitude is V0 by root 2. We know that this is the capacitance. I am writing its reactance divided by the magnitude of the overall impedance, which is, because we know that this is an imaginary quantity which is having a j term. So let us see how do we got this as 999.9, all those stuff. So let me just tell you the use of calculator also, effectively how you can able to use a calculator. So let me go back here. Okay, we have this as a circuit. Let me rewrite that. This is, I will write the simplified one, which is 10.1 microfarad. This is C equivalent, and this is the resistance. So the resistance was 1 kilo ohm. So this is, okay, let us say it as Vs, which is nothing but V source. This is V0 here. Now let me represent this by the reactance. So now V0 is equal to, it's like, okay, current multiplied by the reactance offered by, sorry, it is the current multiplied by the reactance offered by this. So the current, we know that it is Vs divided by the overall impedance is, it's actually so shall I write it as Z, and of course this is XC, this is XC. So we know that this is actually having R plus, of course we have the XC also. So what is XC now? XC is actually equal to minus J 2 pi F into C equivalent. So this is what is the magnitude is. So coming to the actual value, so since we don't know what is the frequencies, let us write the magnitude of this as Vs by under root of, okay, this is XC square plus R square into XC, just the magnitude. So what is the magnitude of this? This is actually, just write it as 1 over 2 pi F into C equivalent. So now this we know that this is Vs by root 2. So this Vs will go off. So you end up with so you have 1 over root 2 is equal to XC divided by under root of XC square plus R square. So what is R square? It is 1000 whole square. So now let me not simplify anything here, so I will find XC now. So let us see how do we feed this equation as it is. So now you can see it is 1 divided by root 2. This is 1 by root 2, which is this. So I will make it alpha equals, so carefully note it is alpha equals, and then this is xc, which is an unknown. I will just type it as alpha a, this is the unknown parameter, divided by open the parenthesis, open the square root, open again the parenthesis, it is alpha a square plus 1000 whole square, close the parenthesis, shift calculate. So now whatever value that I'll get is corresponding to xc. Now the xc is 1000. So that's how I got this xc as, this is what is given as 999.69 is there, no? So this is approximately equal to 1000. So here okay, why it is not exactly, because now while substituting this 10 by root 2, I slightly approximated 7.07. I didn't put all decimals, so that's why it is coming out like 999.69. But if you write it as 1 over root 2 in full, so you will get it as 1000. So xc is 1000. So that's what you got, xc as 1000. So now when xc is 1000, you will get the output as equal to vs by root 2. So now if you just go here, and try to equate 1000 is equal to 1 over 2 pi f into what is C equivalent? C equivalent is 10.1 microfarad. So now it's very easy to find f now. So what is the frequency at which V0 is equal to 1 over root 2 times Vs? So that I can find. Okay, before that let me just tell this again, how do I got it as so and so. I will again redo it. So maybe you can say root 2 inverse, okay, or you can say root 2 inverse. So this is root 2 inverse is actually like 1 over root 2 alpha equals, so it is, you can open the parenthesis, alpha a divided by, open the parenthesis, square root, open the parenthesis, alpha a square plus 1000 square, close, shift cal. You can see a is coming out to be 1000. That a is nothing but xc. So that's what we are doing now. So now it is 1000 alpha equals, open the parenthesis, 2 into pi into f is now alpha a into 10.1 exponential minus 6, close the parenthesis, whole inverse, shift calculate, I'll get the value of f. So f value is 15.75 hertz. So this is the frequency at which magnitude is 1 over root. Now how do we do the simulation of this? So what you can do, you can again go to the same circuit what we had earlier. So what I'll do, I'll take the same circuit. Now what is this? Okay, in order to make this zoom, you can make it so and so. So now is it 10.1 micro? That is 10.1 micro. This is 1k, this is 1k. We are actually asked to find what is the value of frequency at which magnitude is also. So let us keep the frequency. Okay, what I'll do is let me sweep the frequency. So okay, since we already found it as 15.75 hertz, so let me make the frequency as, okay, how do I do that? You can click on this, you can see, let me make it as 15.75 hertz. if you do this with a magnitude of 10, if I run, output will be 1 over root 2 times input. So what is 1 over root 2? It is 0.707 times of 10, which is 7 points also. And of course I can also find what is the phase shift at that point. So let us do that later. Let me run now. Okay, now what I'll do is, okay, why it is not coming is because my time is not sufficient. That is, this time will not be sufficient to show one complete cycle. Let me just make it. What is the time period of 15.75 hertz? It's actually 63 millisecond. So let me make it as 100 millisecond or make it as 500 millisecond so that I can get at least few cycles. I will run now. You can see you are getting few cycles. So input is 10 volt peak. Peak to peak is 20 volt. If you see the output, it will be 7.07. Just see here. See the output. Let me just zoom it. If you go to the peak is 7.07. See here, 7.07, because 7.07 is 10 by root 2. So now you can clearly note that the input peak and output peak are not coming at same time. So actually output peak is coming bit late. So there is a phase lag. We can actually find out how much is the phase lag. So as we did in the earlier case also. So what is phase now here? If you can actually see what is the phase, as we found, okay, what is, if you want to find the phase of it, what is, now I will write the complete expression, not just the magnitude. If I write the complete expression, V0 is equal to Vs, what is XC? It is minus J 2 pi F into C equivalent divided by, okay, it is, okay, under root of 1 over 2 pi F C equivalent whole square plus 1000 whole square. The phase part of this is tan inverse of what is this? So it's actually, now it is okay, XC by R. So here it is, the phase part of this is, the magnitude is this 1 over 2 pi FC, which is 1000 by the root of 1000 square plus 1000 square. This is 10, okay, 10 sine so and so, 10 sine 2 pi FT. Of course plus phase is this, so this is actually minus 90 degree and minus of tan inverse of this is actually 1000 by 1000 is tan inverse of 1. Tan inverse of 1 corresponds to 45 degree. So this is actually this is minus 45, minus of minus will become plus, and this is now phase of minus 45 degree, meaning the output will be 7.07 sine 2 pi 1000 t minus 45 degree. So this is V0. How do you got this minus 45 degrees? Because here the phase is what? Tan inverse of minus 1000 by 1000. So tan inverse of minus 1 is minus 45 degree. When it goes up here, it will become plus 45 degree. So it is minus 90 degree plus 45 degrees minus 45 degree. So this is the thing. So now the output voltage is having a magnitude of 7.07 at a frequency of 1000 hertz. The phase is minus 45 degree. So that you can see here in the simulation result. How do I show you the phase shift here is, okay, I'll just show you how to find the phase here also in the, I'll just do this here. Can you see how much is the time period for, so this is from here to here, it is 180 degree. because from here to here is 180 degree. How much is the time? The time corresponding to, okay, you can see, let me just say that for 180 degree the time is 309.66 millisecond. That's what we have from, maybe let me just go to the exact peaks here. So this is from here to here. This is, that's what is 308. Actually, how we are getting this time, 360 degrees full cycle, it's actually half of this time. It is 15.75 by 2 is that much, 1 over that is 126. You can see this is the where is the difference of time. Sorry, difference of time is actually 31.6 millisecond. So 180 degree corresponding to 31.6 millisecond. So how you got that as? It is 15.75, 1 over that by 2. This is how you got it. Let me just tell you. So from this peak to this peak, it is 1 cycle. This is total time period. Since the frequency is 15.75 hertz, time period is 15.75. 1 over is, in terms of millisecond, it is 63.49 millisecond is from here to here. But from here to here, this is actually 180 degree phase shift. For 180 degree, it is half of this time, so that is divided by 2. Can you see it is 31.74 millisecond. That's what I got it here, 31.6 millisecond, which is there here, 31.6. It's the difference between this and this. Now let me just take the difference between the peak of input and peak of output. See, now this is the peak of input. Let me take this and okay, let me keep it here. This is okay, input peak is there. Let me take this is input. Channel 1 is input. Sorry, cursor 1. Cursor 2 is output. See, now am I putting one at the peak of this, other is at the peak of this? How much is the difference in time period? It is 7.7. The time period is 7.95 millisecond. What I am trying to say is 180 degree phase shift corresponds to 31.74 millisecond. 3.95 millisecond corresponds to want phase shift. So that's very easy. So what you can do is, it's 180 into 7.95 divided by 31.74. Can you see it is 45 degree? Can you see this corresponds to 45 degree now? So that is the way how you can able to find the phase shift of the signal in the waveform also. So I am just putting one cursor here at the peak, the other cursor over here. Can you see the output is coming after some time? What is the time? That time is 7.95 millisecond. This time corresponds to actually 45 degree lagging, 45 degree lagging in terms of degrees. So we can exactly get the same result if I do a frequency response. So what is this frequency response is? Let me go here. Instead of having a single frequency, I will have, okay, now let me make this as none. Let us make it as an AC source, and I will change this to an AC analysis. Now let me sweep the frequency. So this is 100. let me start from 1 Hertz, go up to 1000 Hertz and say, what is this? Now let me run. See now, when I'm running, see now this is, can you see this is the magnitude and the phase? Okay, this, let me just take out this. Okay, cancel. Let me again run. When I run, I will find this output. Now you can put two cursors. So how much is this is, okay, let me just start from bit lower frequency. Instead of 1 Hertz, let me start from 0.1 Hertz, 0.1. I'm again running. So I'm running from a very low frequency, 0.1 Hertz. You can see output voltage almost 0 dB. At a frequency equal to, okay, now let me just go for, when the phase shift is 45 degree, we are looking for a frequency of 15.75 Hertz. So you just have a look at this frequency. So when that is 15.75 Hertz, so just keep an eye on this frequency. When it is 15.75 Hertz, so are you having an eye? It is 19 now, 18, 17, now it is 16, okay, now 15.75, and they're very close to it. Okay, see here, it is 15.75 Hertz. See the magnitude. Magnitude is minus 44.95, which is equal to minus 45 degree. So that's what we saw here, no? That's what we saw here. So when the frequency is 1000 Hertz, the magnitude is, okay, I'll come to this. Magnitude is 7.07. The phase is minus 45 degree. So now what is this actual V0? So V0 is V in times, V0 is V in by root 2 times. Suppose if you take the magnitude of this as 1, is it not 1 over root 2? What is 1 over root 2? It is 0.707. So it is 0.707 is V0 if V in is 1 volt. So actually we have taken the input as 1 volt, no? We have taken the input as 1 here. So let us take the input as 1 here, a unit 1. If it is 1, then it is 1 over root 2. If you carefully note this signal here, the y-axis is actually in terms of dBs. So what is this dB? It's actually decibels. We represent in frequency analysis or in AC analysis, the dB is nothing but decibels, 20 log of V0 by Vin. So what is V0 is equal to, V0 is 1 over root 2 times Vin. Suppose if I write 20 log of 1 over root 2 times Vin by Vin, does this go off? So do you have 20 log of 1 over root 2? So we are talking about the magnitude of the output, magnitude of the output by input. So what is 20 log of 1 over root 2? If you see the magnitude, that is 20 log of root 2 inverse. Root 2 inverse is actually minus 3 dB. This is minus 3 dB. That is at frequency is equal to 1 kilohertz, 15.75 hertz. Magnitude is minus 3 dB, which corresponds to 1 over root 2 times of Vin, and the phase is minus 45 degree lagging compared to input. All these information are captured here. See, it has got two plots. So this is dotted one, which indicates the change in phase, the solid one which indicates the magnitude. So in a frequency response, in AC analysis, we will get two plots. One is called as magnitude plot, other is phase plot. in polar quantities, I think all of you know that in polar we always have magnitude and phase. So what are the magnitude? So magnitude is okay, in this case it is xc divided by xc square plus r square. What are the phase? It's minus 90 degree plus of tan inverse of xc. So this is what you have, xc by r. So this is the phase part, this is the magnitude part. So as the value of f changes, this is changing, this is also changing. So naturally the magnitude also changes, phase also changes as the frequency of the input signal changes. So that's exactly being represented here. You can see as frequency is changing from 100 millihertz to 1 kilohertz, the magnitude is changing, phase is also changing. So the intention here in this problem was, we were asked to find at what frequency the magnitude becomes 1 over root 2, that is, what is that, 0.707 here it becomes 0.707, that is 1 over root 2 times the input. So that is coming out to be 15.75 hertz. So that's what we are again confirming that. So at a frequency equal to 15.75, magnitude is 1 over root 2 times, which is nothing but minus 3 dB. Why it is minus 3 dB? You can see 0.707 in terms of dB is actually minus 3 dB, which is happening at a frequency of 15.75 hertz. So this captures both the magnitude as well as the phase, Okay, forget about this magnitude here, this cursor, maybe a single cursor is enough. You can just say this is, if you run it again, take one cursor, place such that it is at 15.75 hertz. That is 15.75 hertz. So you can see this is 15.75, magnitude is minus 3 dB, and the phase is minus 4. On the same lines, we have the other example, but there the resistance capacitors are interchanged. Again we are just equating these to 10 by root 2. So now here it's actually R. This is R multiplied by the current. R and V by this is the current. Suppose if you equate this to 10 by root 2, solve for this XC, that becomes so and so. So that we can try again here. So what I'll do, I will just move this. I'll take out this and control R. Okay, I'll put this here. It is W. I'll wire it. Okay, it is done, and then I'll again move this. So for moving it is, maybe simply type it as M. I can move it. So let me control R. Okay, let me have a look at is it. Okay, fine. So it's fine now. So the resistance value is actually 10K, that is this is 10K, and this is 0.909 microfarad. I think these are the values. Now if I run this, okay, I have specified, okay, this is so and so. Now at 17.5 hertz I have to get minus 3 dB, and the phase should be, let us see what is the phase. Interesting. So if you can see now, since there is nothing over here, so if I write the expression for the output voltage, so now you can see what is V0 is equal to V in. Okay, this is R by under root of XC plus R. Actually this is V in R is actually 10k divided by, this is under root of this is xc, no, xc is 1 over 2 pi f into, okay, this f into c plus 10k, this is equal to v in by root 2. This v in will go off. If you substitute, okay, sorry, this is actually square, this is again square, this is actually c equivalent. Now if you solve for this, of course here also you can get the value of f directly. So it is now 10k divided by under root of, okay, it is 1 over 2 pi f into c equivalent whole square plus 10k whole square is equal to 1 by root 2. Solve for f. If you solve for f, you will get the value of f as 17.05 hertz. How about the phase? You can see here the phase part is not there in the numerator. The phase part is not the numerator, only phase part is there here, which is nothing but 1 over tan inverse of minus xc by r. Since x and r will be same, so this will become 1 over tan inverse of minus 1, which is actually 1 over phase angle is 45 degree, minus 45 degree. If it goes to above, it will become 45 degree plus. So actually V naught is, okay, 7.07 sine 2 pi f is how much? 17.05 into t plus 45 degree. So this will be having a phase lead of 45 degree. It's actually coming earlier. The output is coming earlier than the input. That's what we call it as phase lead. That we can see it here now. See now. Let me just put them apart so that you can able to see them properly. This is the output, and you can see this is C value, this is R value. If it is confusing, let me just put this here. Okay. Now if I run, okay, I'm running from 0.1 hertz to 1000 hertz. So at 17.05 hertz, that you can see here. See now, at this, just have a look at this frequency 17.05 hertz. See, is it now 17.05? Are you very close to that? See this. See this. So this is 17.05. Can you see it's almost 45 degree? Can you see it is plus here? See, interestingly, the magnitude. Can you see the magnitude is exactly 3 dB down, minus 3 dB down. So it's minus 3 dB down means it is 0.707. So magnitude is V in by root 2, which is minus 3 dB, and the phase is plus 45 degree. So that's what is seen here. So phase is plus 45 degree and the frequency is 17.05 hertz. So if you want to see the waveforms, you have to replace this by a sine wave of magnitude 10 volt, make it as 17.05 hertz. If you do this and if you do the transient analysis, now the analysis should be transient. Okay, now let me make this transient analysis. When this becomes blue, that is like, okay, it's a text. So if it is black, it will be a command. So blue is a text. Here you can see here, this is text. So placement of text is in blue color. So this is not used as a command. Now this is used as a command. If I run it now, you can see I'm getting the output signal. Let me compare the output with the input. Output will be actually leading the input. So it's surprising to see, before you get the input, the output will be coming earlier. So how do I do that? So So this is output. I want to trace the input also. Add trace, which is V in. You can see I'm adding the input. What I'll do, I will put them in two different panes. You can see the blue one is input, blue is input, green is output. Can you see you are getting green peak earlier than the blue peak? So this is output, this is input. Can you see this peak of green is coming earlier to blue? So it is phase leading. If I just bring this here, like, can you see this is green one, its peak is coming, whereas the peak of your input is coming late. So that's why we say output is in phase lead with the input signal. So in case of these type of RC network, because RC, if you have a capacitor followed by resistor, then output phase will lead the input, whereas in the previous case output phase was lagging the input. By how much phase? That depends on the frequency. So for a frequency 17 point whatever 5 hertz, so we have a phase lead by 45 degree, phase lead by 45 degree. So that's what is seen here, that's what is seen. Can you see now? Maybe you can able to make out if I just have at least 2 or 3. See now, this is output is in green color, input is in blue color. Input comes here, before that you are getting the output, So this is what is interesting in electronics, phase lead and phase lag. In the previous case we saw the phase lag. Of course, if I change the frequency, if you can see, if I increase the frequency, suppose if I increase the frequency to 100 hertz or maybe 1 kilohertz, you can see output and input are in phase. So that also I can show you that. So you can see this is coming earlier to input. So let me change the frequency and interestingly see what happens. So where is that? I can put it here. I will make the frequency maybe, let me add 2 zeros. Now I just increase the frequency 100 times. If I run it, oh, interestingly you can see there are so many cycles. So now let me stop it here, and then if you see this, actually both the waveforms are there overlapped, that's why you cannot see that. So if you want to see it clearly, let me just put it in different panes. So input output, see this very clearly. Are they exactly in phase? You can see whenever the output peak is there, input peak is also there. So there is no phase shift. So as I said, the phase shift not only depends on R and C values, it also depends on the frequency. I can see the input and output are at same phase at higher frequency. Suppose if I reduce the frequency to maybe 1.75 hertz, you can see I'll make it 1.7 hertz, 1.7 hertz. Now you can see interestingly what happens. At 17.05 hertz, it was 45 degree phase shift, that is phase lead. When it was 1700, there was no phase shift. I am reducing the frequency 10 times. You interestingly see what is the phase shift. Now the frequency has been reduced. Okay, sorry, what happened? Let me save this and run again. I'm not getting all the number of waveforms because the time period is not sufficient. I may have to change the time period to another 0. Now you can see. Okay, I will not get it because let me just slightly increase this time step to maybe around milli. These things you'll get it in coming days. See now? Now you have this. Interestingly, see now the phase lead of your output is far more greater than 45 degree. See now, where is the input? See, this is your output peak, input peak is here. This is your output peak. Can you see this is your input peak? Can you see it is coming so early compared to input signal? So here the phase shift will be more than 45 degree. Maximum phase shift you'll get is 90 degree in this RC network. So here the phase shift is more than 45 degree for very low frequencies. For frequency of 17.5, the phase shift is 45 degree. When the frequency is very high, there was no phase shift. So it purely comes from this equation, because this is my phase shift. Phase shift is xc by r. Xc changes with frequency, so this tan inverse of quantity will also change. So this minus 45 degree can be minus 60 degree, it can be minus 20 degree, or it can be 0 degree. So the phase shift is plus 45, plus 0, plus 10, plus 60, plus 80, not more than 90 degree phase shift. Okay, these are the interesting things what we lined up. This is what is electronics is. So if you can see, without the input, before you get the input, your output is already there. So we call it as phase lead, phase lag in the previous case. So these are the interesting things which you'll be seeing in the coming classes. Thank you.